Hello and welcome to the last day of the pre-course. My name is Ulrik Beierholm. I am going to talk about probability and statistics today. Who am I? I'm the day lead, obviously, for the same mentioned topic in the pre-course. During the daytime, I'm an assistant professor at Durham University in beautiful northeast of England, and I studied perception and decision making using behavior, fMRI and EEG, and I love music, comic books, and my family, which thankfully loves the very same things too. So, in computational neuroscience, we rely on probability and statistics a lot. You can build up probabilistic models in order to explain things as diverse as single neurons, as neural networks, animal behavior, groups of different animals or people, and it's an extremely useful tool in order to be able to do modeling with. And not only do we use it to build models, we of course use probability and statistics also to analyze any kind of experimental data that we have, and we can use statistics then to evaluate any kind of models that we have. So we tend to rely a lot on these concepts, and it is something that you'll see over and over again within the course. So for today, the topics that we'll be covering includes things like stochasticity and randomness. We'll talk about different types of probability distributions, a little bit about probability theory. We'll talk about some classical maximum likelihood inference, as well as Bayesian type of inference too. And by the end of today, you should have some intuition about how stochastic, randomly generated data actually work. You should understand a little bit about how to model data using very simple distributions. You should understand some of the differences between discrete and continuous distributions, and be able to plot a normal or Gaussian distribution too. You should understand what the likelihood function is and why it's important to use. How to summarize the Gaussian distribution using mean and variances, and know how to maximize a likelihood function. And lastly, you should be able to do a little bit of simple inference in a classical as well as in a Bayesian type of way. So let's get started. First tutorial, section 1. It's a stochastic world. We might as well just jump straight into it. There's no getting around that the world really is stochastic. Partly that might be because of our lack of knowledge. If you're rolling a die, maybe it's something that you can predict on a quantum level, maybe not. That's an entire different type of discussion. But certainly from our viewpoint, we do not have access enough to the knowledge about the world to be really able to think about it in practice being deterministic. So from our viewpoint, it's a stochastic world that we have to deal with. And that manifests on many kind of levels. For neuroscientists, that means that firing of single neurons can be very hard to predict. Activity in a cortical column in the brain would be hard to predict. The behavior of an animal are hard to predict, and so on and so on. And because of these things, we need to take into account this uncertainty that we have. And if you're in a stochastic environment, then you need to move into some kind of probabilistic framework. That means you need to have some kind of models. You need to have a generative model that specifies what's the assumptions that you have about properties of the world, and then giving rise to different observed data that you see. So it allows you to quantify that kind of relationship between those two, between the data and between the world property. And the critical thing here is that it's not a perfect one-to-one mapping. So you can have a state of the world giving rise to a property, giving rise to a data that you observe. So here I call them theta 1, giving rise to x1. But there can be other states of the world that can give rise to the exact same data. So you can't necessarily be able to directly infer one kind of in a one-to-one simple mapping based on this. And if you've studied any kind of perception in psychology or neuroscience, then you'll mean tons of examples like this where, say, a three-dimensional world is being reflected onto a two-dimensional retina, and therefore you need to do inferences about what's actually out there. And that's something we will talk about later today. But let's start with something simple. Let's start with some simple examples of what it means to have something be random. And one of the simplest distributions you can think of is just to have a uniform distribution. So if you look at the plot up on the right, there's a variable x that has an equal chance of being given one of these values within a certain range, and outside of that range there's zero probability of having it. So that's referred to as the uniform distribution, and often is written out in this kind of way here. So it's kind of flat in between 2 points A and B, and 0 outside of that. And one thing to realize, of course, with randomness is that just because something is distributed randomly according to a specific function or specific distribution, it doesn't actually mean that it's always going to be kind of spread out in a nice way according to that. So, if you have few samples, for example, you might find that they're not actually spread around nicely, and instead they will be random. So having some intuitions about what randomness means is important. And in the first exercise that you'll be doing, you will indeed be trying to do some sampling from the uniform distribution and get a little bit of a feel for how random can it actually be. So good luck.